Usually when we consider how our brain interacts with the physical world, we default to this expectation of a direct, high-fidelity feed.
Right, like a perfectly focused camera lens.
Exactly. Like you look at a coffee mug on your desk, the photons hit your retina, the signal fires up the optic nerve into your visual cortex, and your brain simply points and says, there it is, a mug.
Yeah, it feels binary and immediate. The subjective experience is one of like a perfectly insulated cable piping reality directly into your conscious mind without any loss of fidelity at all.
But the moment you step into the actual neurobiology of perception, that illusion of the clean camera lens just shatters completely.
It really does. It's covered in static.
But the sensory landscape the brain is dealing with is incredibly murky. I mean, the brain never actually sees the physical world. It is trapped in a dark vault.
It only ever perceives its own noisy electrical chatter.
Yeah, and from that continuous static, it has to construct a reality, which is wild.
It is.
And the craziest part for you listening today is that every single choice you make, what to eat, when to cross the street, who to trust, is just your brain placing a calculated bet on which static is the loudest.
That is exactly the fundamental premise we're tackling in this deep dive.
So let's unpack this. What are we looking at today?
We are looking at the foundational building blocks of higher thought. We're drawing directly from Chapter 56 of Principles of Neuroscience, which focuses heavily on decision-making and consciousness.
Right, the absolute gold standard text.
Yeah, the goal here is to carve higher cognitive function at its joints, essentially. We need to use neurobiology to understand how we actually process a thought.
And we're starting with the absolute simplest sensory decisions imaginable, right?
Exactly, and then scaling up to the physical threshold of a conscious choice.
To do that, though, we have to throw away our colloquial definition of cognition.
We really do. We casually use the word to mean, well, anything related to thinking.
But neurologically, if we are looking at the architecture of a circuit, cognition is defined by two highly specific types of flexibility.
Right. The first is contingency, and the second is freedom from immediacy.
I want to try and map these onto actual biology for a second. So contingency implies that a stimulus in the environment doesn't automatically trigger like a hardwired reflex, right?
Correct. Let's look at the basic circuitry. Say you touch a hot stove.
Okay, classic example.
The sensory input travels to your spinal cord and immediately synapses onto motor neurons that retract your hand.
So the input mandates a specific, unvarying output.
Exactly. That is a dedicated routine governed by the rigid time steps of nervous transmission. You pull back before the pain signal even reaches your cerebral cortex.
So there is zero contingency there.
None at all.
But if I step outside and feel like a single drop of water hit my arm, I don't violently deploy an umbrella like a spinal reflex.
Right, you don't.
The sensory input reaches the brain, but the motor output is totally decoupled. I pause. I look up at the sky. I wait to see if I feel another drop or if it was just, condensation falling from a tree branch.
And that biological decoupling introduces the second flexibility, freedom from immediacy.
Freedom from immediacy.
Yeah, your internal mental processes, the operations in your association cortices, are transpiring over a time scale that is completely divorced from the real-time demands of the physical environment.
So the raindrop hits you in a fraction of a second, but your processing of that raindrop spans seconds.
Right. Your gathering of additional evidence takes time. You are operating on an internal timeline now.
Okay, so combining those two, contingency and freedom from immediacy, how do we define a decision at the strict neurobiological level?
It's not just a philosophical choice. In this context, it is a provisional commitment to a proposition, an action, or a plan.
And it's calculated by combining three distinct streams of data, if I remember the text correctly.
Yes. Sensory evidence, prior knowledge, and expected outcomes.
The anchor there is the word provisional, isn't it?
It is. In a neural network, a decision is a change in the internal state of the organism.
Like a sustained firing pattern in a specific population of neurons.
Exactly. But it does not necessitate immediate behavior. You can make a decision and never move a single muscle.
You can just change your mind before the motor command is even sent.
Right. It's incredibly useful to conceive of a thought itself as merely a provisional plan of action that has been decoupled from the immediate motor output.
But that creates a massive experimental hurdle for scientists, doesn't it? How do you study something as invisible and provisional as a plan?
It's incredibly difficult. If you put someone in an fMRI machine and ask them to solve a complex moral dilemma, the entire brain lights up.
Yeah, like the trolley problem. It's just too muddy. You've got emotional centers, memory centers, language centers all firing at once.
Exactly. So we have to start at the absolute foundation. We have to look at psychophysics.
And isolate the simplest possible choice an organism can ever make, which is basically, is something there or is it not?
Right. We have to trace this back to the 19th century, to Ernst Weber and Gustav Fechner.
Oh, the founders of psychophysics.
Yeah, they founded the field to measure the absolute limits of sensory systems long before we had electrodes fine enough to record from a single neuron.
Like, what is the dimmest light a human can see? Or the absolute faintest pressure we can feel?
Exactly. And they discovered that under optimal dark adapted conditions, the human visual system can detect a single photon of light.
A single photon. That's the physical limit of the universe.
We are literally as efficient as physics allows. But here is the catch.
There's always a catch.
Every time a subject in that dark room presses a button and says, yes, I saw the light, or no, I didn't, they are making a cognitive choice based on ambiguous evidence.
And this brings us to signal detection theory, right?
Right.
Which fundamentally reconceptualizes the environment the brain operates in.
It really does. Because on any given trial in a psychophysics experiment, the physical world is perfectly binary. The photon was either emitted or it wasn't.
But as we establish, the brain lacks a direct window to that binary physical truth.
Right. It relies entirely on a neural representation.
Yeah.
And that neural representation is intrinsically biologically noisy.
Okay, let's drill into what we actually mean by noisy at the cellular level. Because we aren't talking about, like, static on a television screen.
No, we are talking about the basic biophysics of cells. Neurons are essentially bags of salt water and proteins.
Right.
They are subject to thermal noise. Ion channels randomly flicker open and closed. The synaptic vesicles that release neurotransmitters do so probabilistically.
So even if you are sitting in a pitch black, perfectly soundproof room, your sensory neurons are still spontaneously firing action potentials.
Precisely. They have a baseline firing rate.
Yeah.
And if we plot this mathematically, we get two overlapping probability distributions.
Okay, let's visualize this for the listener. Imagine a graph where the horizontal axis is the firing rate of a group of visual neurons, say, spikes per second.
And the vertical axis is the probability of that firing rate occurring.
Got it. So in total darkness, your spontaneous neural chatter creates a bell curve.
Right. Most of the time, the neurons fire at a low baseline. But occasionally, just by pure biological chance, a bunch of ion channels open simultaneously.
And the neurons fire a rapid burst.
Exactly. We call this entire bell curve the noise-only distribution.
Then the experimenter introduces the weak stimulus, a single photon.
The retina catches it, the signal propagates, and the neurons fire a bit faster.
But because the stimulus is so incredibly weak and the baseline cellular noise is so highly variable, this photon doesn't cause a massive, undeniable spike in activity.
No, it just creates a second bell curve, the signal plus noise distribution. And it's shifted slightly to the right of our baseline curve.
The absolute core of the decision problem here is that these two distributions overlap.
Yes. When the brain evaluates the visual cortex, it doesn't get to look at beautiful, clean bell curves.
It just gets handed a single momentary sample of evidence, just one number.
Right. Let's say the visual cortex reports a firing rate of 20 spikes per second. The brain has to decide, did that 20 spikes per second come from the high end of the noise-only curve?
Or the low end of the signal plus noise curve.
Exactly. Because 20 spikes per second falls right in the middle of the overlap, absolute certainty is biologically impossible.
So the brain is forced to enforce a decision rule. It has to draw a line in the sand, a criterion threshold.
Yes. If the incoming evidence is 21 spikes per second or higher, the brain's rule dictates we say, yes, I saw light. If it's 19 spikes, we say no.
This model is so elegant because it separates two entirely different phenomena. First, the reliability of the evidence, and second, the strategy of the decision maker.
What's fascinating here is how the physical separation between the peaks of those two bell curves dictates discriminability.
Which is mathematically represented as D prime, right?
Yes, D prime. If the stimulus is a bright flashlight, the signal plus noise curve shifts massively to the right. The overlap vanishes, D prime is large, and the choice is trivial.
But the criterion where the brain places that threshold line dictates the policy of the decision maker.
Yes, policy is the key word. The textbook uses a medical analogy here to illustrate policy, which I think is crucial.
Oh, the mammogram analogy. Imagine reading the calcium density scores on screening mammograms.
Right. Healthy tissue naturally has a range of calcium density. That's our noise-only curve.
And tumors generally produce higher calcium scores, so that's our signal plus noise curve.
But again, biology is messy. The curves overlap. Benign cysts might have high scores, and some tumors might have unusually low scores.
So as the radiologist establishing the diagnostic protocol, where do you place your criterion?
Exactly. If you place the threshold very low, a lax criterion, you ensure that you catch almost every actual tumor.
That gives you a high hit rate.
Yes, but mathematically, because your threshold is so low, you are sweeping up a massive portion of the healthy tissue distribution that just happens to be on the higher end of normal.
Meaning you are generating a massive amount of false alarms. You're telling healthy patients they might have cancer.
Right.
Wait, I want to challenge the terminology here for a second. Calling that functional noise sounds like a very convenient way to brush human error under the rug.
How do you mean?
Well, if a doctor misses a tumor because their threshold is set differently or because they were just tired, we don't call that biological noise. We call it a misdiagnosis. Are neuroscientists just using noise to excuse variance they can't explain?
That is actually a fundamental debate in the philosophy of science.
Oh, really?
Yeah. But in the context of signal detection theory, noise is not a scholastic debate between chance and determinism. We are not saying the universe is fundamentally random.
Okay.
We're defining noise functionally. It is any source of variance in the internal representation of evidence that the decision maker fails to account for, which ultimately leads to an error.
So if the radiologist was tired and that fatigue lowered their visual acuity, that fatigue acts as functional noise within the system.
Exactly. And the ROC curve, the receiver operating characteristic curve plots, hits against false alarms across every possible criterion.
And what does that curve prove?
It mathematically proves that you cannot magically increase your hit rate without also increasing your false alarms, unless you fundamentally improve the D prime.
Ah, meaning you have to improve the quality of the raw evidence itself.
Right. If the raw evidence remains exactly the same, the divergence in choices between two people, or even the same person on two different days, comes down entirely to a shift in policy.
Their internal risk-reward calculation moves the threshold. Like, if the cost of a miss is a patient dying, you accept the high false alarm rate. You move the line to the left.
Exactly. And if the cost of a false alarm is an instantly lethal, highly dangerous surgery, you move the line way to the right. You accept more misses to ensure you never operate on a healthy person.
Okay, I see. So translating that back to simple neurobiology, a yes-no detection task is merely the ground floor.
It is. It relies on evaluating a single stream of evidence against a static background.
But real-world cognition rarely works like that, right? We are constantly forced to choose between competing alternatives.
Right. The question rapidly evolves from, is a stimulus present, to which specific stimulus is it?
And to trace how the field of neuroscience made that leap, from studying simple detection to studying active deliberation between competing sensory inputs, we have to look at the work of Vernon Mountcastle.
Yes. He ran a truly pioneering experiment using somatosensation, the sense of touch.
He trained monkeys to categorize the frequency of a mechanical flutter applied to their fingertips, didn't he?
He did. The physical intensity of the vibration was strong, so there was absolutely no ambiguity about whether the stimulus was present or absent.
So the basic detection problem was already solved.
Exactly. The cognitive decision was strictly about the quality of the flutter. Is it a high frequency or a low frequency?
And the trial structure was strictly sequential. The monkey would feel a reference vibration on its finger. Let's call it F1.
Right, and this F1 was always exactly 20 cycles per second, or 20 hertz.
The monkey feels this 20 hertz buzz, and then the probe pulls away. There is a delay of several seconds of complete stillness.
Then, the probe comes back and delivers a test stimulus, F2.
Which might be 10 hertz, or 25 hertz, or 30 hertz.
And the monkey's task is to press a button indicating whether F2 was faster or slower than their memory of F1.
Conceptually, Mountcastle hypothesized that the brain could solve this using the exact same overlapping probability distributions we just discussed, right?
Yes, but instead of noise versus signal, the distributions represent the variable neural firing rates triggered by a 20 hertz physical vibration versus, say, a 22 hertz vibration.
Because of the thermal and synaptic noise we discussed earlier, a 20 hertz flutter might sometimes produce a neural response that looks like 22 hertz.
Right. The overlap remains.
So Mountcastle proposed a mathematically elegant subtractive model.
He did. The theory was that the brain takes a neural sample of F1, holds onto it, takes a neural sample of F2, mathematically subtracts the two values, and simply looks at the sign of the result.
So if F2 minus F1 is positive, choose faster. If it's negative, choose slower.
It is brilliant in its simplicity. Yeah. But when Mountcastle placed electrodes into the primary somatosensory cortex and the thalamus of these monkeys, he hit a biological brick wall.
What happened?
He found primary sensory neurons that were perfectly phase-locked to the mechanical flutter. If the probe vibrated at 20 hertz, the neuron fired 20 action potentials per second.
So the raw data was there, the sensors were working perfectly.
Yes, but the neural architecture completely failed to support his subtractive theory.
Because for the subtraction to happen, the brain needs both numbers at the same time. The F1 vibration happened and then it stopped. There were seconds of empty silence before F2 arrived.
Exactly. Mountcastle was looking for a population of neurons that would keep firing, holding the memory of that 20 hertz F1 reference throughout that silent delay period so it could be compared when F2 arrived.
And he couldn't find them.
He couldn't find them. The neural responses in the primary somatosensory cortex decayed the millisecond. The physical probe was removed from the skin.
Oh.
Yeah. The network architecture of early sensory cortices simply lacks the extensive recurrent excitatory connections required to sustain persistent activity without continuous sensory input.
So without a biological trace of the reference stimulus persisting through time, he couldn't observe the actual comparison happening. The mechanism of the decision remained entirely invisible. This is actually one of my favorite pivots in the history of neuroscience.
It's a great one.
Because when a mathematically sound theory hits a biological wall, the solution isn't usually to force the biology to fit.
No, you have to redesign the game.
And that's what William Newsom did. He looked at Mountcastle's roadblock and realized the memory requirement was the fatal flaw.
So Newsom eliminated memory from the equation entirely by switching from the sense of touch to the sense of vision.
He developed what is now a legendary behavioral task, the random dot motion discrimination task.
Yes. He presented monkeys with a field of dynamic random dots moving on a computer screen.
And the decision was no longer sequential. The monkey simply had to look at the screen and decide, is the net overall motion of this field of dots moving to the right or to the left?
The genius is in how the stimulus is controlled via a metric called percentage coherence.
Right. If you set the screen to 0% coherence, every single dot is appearing and disappearing in totally random locations, frame by frame.
It looks like pure television static, or a chaotic swirling blizzard. There is absolutely zero unified directional movement, pure visual noise.
Conversely, at 100% coherence, every single dot is translating smoothly and uniformly to the right. It is a solid wall of motion.
But Newsom could titrate the difficulty by testing intermediate levels.
Like 5% coherence.
Exactly. At 5% coherence, 95% of the dots are pure random noise, but a tiny 5% fraction of them are subtly shifting to the right in tandem.
It creates a very weak, ambiguous sense that the static is drifting. It's like standing in a blinding snowstorm where the flakes are swirling violently in every direction and trying to figure out which way the overall wind is blowing by staring at the chaos.
That's a perfect analogy.
So why did this specific spatiotemporal puzzle allow us to crack the neural code of decision-making when the fingertip flutter failed?
For three profound reasons. First, the task fundamentally requires the integration of visual information over both space and time. You cannot look at a single dot.
You have to evaluate the entire population of dots over several hundred milliseconds to extract the weak signal from the noise.
Yes. Second, the exact same population of direction-selective neurons in the visual cortex is recruited to solve the task, regardless of whether it is incredibly easy or impossibly difficult.
So the biological hardware is constant, only the signal-to-noise ratio changes.
Exactly. And third, to your point about Mountcastle, there is no temporal gap. The evidence for left and right is presented simultaneously, continuously, in real time.
The subtraction can happen instantaneously.
Exactly.
So Newsom engineered the perfect cognitive trap. But where in the physical wetware of the primate brain do we actually find the neurons computing this blizzard?
We have to follow the visual processing stream. The raw photons hit the retina, the signals pass through the lateral geniculate nucleus of the thalamus,
Right, the relay station.
and arrive at the primary visual cortex, or V1, at the back of the brain.
And V1 neurons act as basic spatiotemporal filters. They are tuned to detect simple edges and orientations.
But they don't solve the global motion problem. To extract the net direction of the entire dot field, V1 neurons project their signals forward to a higher-order visual area known as the middle temporal area, or area MT.
Area MT. This is the engine room of motion perception.
It really is, and what makes it unique is its architecture. Almost all of the neurons in area MT are exquisitely direction selective.
And they are arranged in columnar structures, right?
Yes. All the neurons that prefer motion moving at exactly 90 degrees to the right are physically clustered together in a column of cortical tissue.
Let's examine the biophysics of a single MT neuron during Newsom's task, looking closely at the data represented in figure 56-4 of the textbook.
Okay, imagine we have a microelectrode recording from an MT neuron whose preferred tuning direction is strictly rightward.
If we show the monkey 100% coherent rightward dot motion, this neuron's firing rate skyrockets. It bursts with action potentials.
But if we show a strong leftward motion, its non-preferred direction, the neuron doesn't just stay quiet.
What does it do?
Its baseline firing rate is actively suppressed below normal resting levels, likely due to GABAergic inhibition from neighboring interneurons.
Oh, wow. So it's being actively silenced.
Exactly.
The crucial observation, though, is what happens when you show that same right-preferring neuron the 0% coherent stimulus, the pure directionless static. The dots are completely random.
Because random noise mathematically contains momentary streaks of motion in all directions by pure chance, the right-preferring neuron will catch glimpses of rightward movement in the static.
Consequently, it fires slightly above its resting baseline.
Right. But crucially, sitting right next to it, a left-preferring MT neuron is also catching random leftward streaks, and it too is firing slightly above baseline.
And right there, we have isolated the physical manifestation of our overlapping probability distributions.
We have found the neural source of the evidence.
Because these two opposing pools of MT neurons, the right preferring and the left preferring, are active simultaneously, the brain can execute a continuous real-time subtraction.
Yes. The decision variable is defined mathematically as the difference in the mean firing rates between the pool of right-preferring MT neurons and the pool of left-preferring MT neurons.
So if the rightward pool is firing, on average, faster than the leftward pool, the mathematical difference is positive, and the downstream decision circuits interpret that as evidence for rightward motion.
Precisely. But as neuroscientists, observing a correlation between MT firing rates and the monkey's behavior is not enough.
Right. Correlation isn't causation. We have to prove that these specific MT neurons are the actual authors of the monkey's decision.
And how do you prove that without completely disrupting the brain? You can't just lesion the entire visual cortex.
Newsom used microstimulation, which is incredibly delicate.
Extremely. Because the MT neurons are anatomically stacked in columns based on their preferred direction, Newsom could lower a microelectrode directly into the center of a right-preferring column.
While the monkey was staring at the random dots.
Yes, and he would inject a microscopic electrical current, barely enough to affect a 50-micrometer radius of tissue.
We need to be very clear about the biophysics here. This is not electroshock therapy.
No, the current is on the order of microamperes. It is so weak that it does not induce a visual hallucination.
If the monitor was turned off, stimulating the MT column produced no behavioral response at all. The monkey only reacted when the ambiguous sensory stimulus, the dots, was present.
But when the dots were present, the microstimulation profoundly biased the monkey's choices.
If the electrode was in a right-preferring column and Newsom applied the current, the monkey suddenly chose right at a significantly higher rate than its baseline performance would predict.
The electrical current was artificially depolarizing those specific neurons, injecting a few extra action potentials into the rightward pool.
And the brain weighed those artificial electrical spikes exactly the same as biological spikes driven by real photons.
It is a stunning proof of causality. But the textbook highlights a critically important methodological lesson here regarding the nonlinear dynamics of cortical networks.
What's the lesson?
The microstimulation only demonstrably altered the monkey's behavior during the weak, ambiguous trials, the ones near the monkey's psychophysical threshold.
Ah, right. If you show a monkey 100% coherent leftward motion, the biological signal from the left-preferring MT neurons is absolutely massive. It's deafening.
Exactly. If you try to artificially stimulate a tiny cluster of rightward neurons during that overwhelming biological flood, the network simply absorbs the perturbation.
The rightward artificial spikes are just drowned out by the massive lateral inhibition coming from the leftward pool.
Yes, if Newsom had only run easy trials, the microstimulation would have had zero statistical effect on the choices. He would have falsely concluded that area MT does not drive the decision.
This is a trap that catches a lot of cognitive neuroscience research, isn't it?
It really is. If you do not push the sensory system to its absolute limits into the low signal-to-noise regime where the decision circuits are hungry for any scrap of variance, you will entirely miss the causal links because the brain's robust network dynamics will overpower your experimental manipulations.
That actually brings up a lingering question about those 0% coherence trials.
Huh.
When there is pure noise on the screen, the experimenter still forces the monkey to choose left or right to get a juice reward right, and the computer rewards them randomly 50% of the time.
That's right.
Is the monkey just rolling the dice? Are they consciously guessing, knowing the screen is blank?
No, and this is where we return to our definition of functional noise. The monkey is not guessing blindly. It is faithfully reporting the internal state of its visual cortex.
So during a 0% coherence trial, the empty neurons are firing due to thermal noise and random synaptic fluctuations.
Exactly. On any given trial, purely by chance, the right-preferring pool might fire 22 spikes, while the left-preferring pool fires 19.
The downstream decision circuit monitors this, performs the subtraction, sees a positive value, and genuinely concludes that the evidence points to the right.
The organism absolutely believes its own noisy sensors.
So we have successfully identified the raw data. We know area MT is generating the sensory evidence.
But here is the biological flaw we still have to overcome. MT only provides instantaneous, momentary snapshots.
Right. The firing rates fluctuate millisecond by millisecond. If you are standing in that blizzard, you can't determine the wind direction by looking at one snowflake for 5 milliseconds.
No, you have to watch the chaotic drift for a sustained period to extract a reliable average. How does the brain sum up this momentary evidence over time?
This moves us into the temporal dynamics of cognition, specifically the speed-accuracy trade-off.
Yes, psychophysical laws dictate that a subject's sensitivity to weak motion, their D prime, improves as a function of the square root of their viewing duration.
Meaning, the longer the brain is allowed to observe the stimulus, the more accurately it can extract the true signal from the noise.
Exactly. This mathematically requires that the brain is accumulating or integrating the momentary evidence from area MT over time.
And the mathematical framework used to describe this is called the drift diffusion model, or bounded evidence accumulation.
Let's make this calculus intuitive. Let's use a physical metaphor.
Okay, imagine two tall glass cylinders or buckets sitting side by side. One bucket represents the decision to choose left, the other represents choose right.
I think this mechanical analogy works really well to explain the math. Let's map the variables.
The leaky pipe suspended above these buckets is area MT.
And every millisecond, the pipe drips water. A single drop represents a burst of neural spikes, a quantum of momentary evidence.
Because MT is noisy, the drops are erratic. One drop falls into the right bucket, the next falls into the left bucket.
But if the screen is showing 10% rightward motion, the pipe is physically angled slightly toward the right.
Drops are still splashing into both, but on average, slightly more drops accumulate in the right bucket over time.
Crucially, in the drift diffusion model, these two accumulations are structurally anti-correlated.
Wait, what does that mean in our analogy?
It means evidence favoring the right is simultaneously treated as evidence against the left.
So as the water level rises in the right bucket, a mechanical linkage physically lowers the water level in the left bucket.
Yes. The difference between the water levels performs what statisticians call a biased random walk. It steps up and down chaotically, millisecond by millisecond.
But it possesses an underlying drift rate that drives it toward the true direction of the stimulus.
Exactly. But the accumulation can't go on forever. You have to eventually act.
This is where the model introduces stopping bounds. Inside each bucket, there is a physical line drawn near the rim.
And the entire cognitive process terminates the exact millisecond. The water level in either bucket hits that threshold line.
If the right bucket hits the bound first, the monkey immediately flicks its eyes to the right.
And this bounding mechanism is what elegantly resolves the speed-accuracy trade-off we mentioned. It entirely depends on where the brain places those threshold lines.
If a situation demands immediate action, say you hear a predator in the brush, you cannot afford to integrate evidence for 3 seconds.
I know. You adopt a policy of urgency. You use very shallow buckets. You set the stopping bounds extremely close to the baseline.
Right. If the bounds are tight, it only takes a tiny net accumulation of drops to hit the threshold. Your reaction time is blistering.
But the mathematical consequence is severe error vulnerability. Because the bucket is so shallow, a totally random burst of neural noise, 3 stray drops falling into the left bucket just by chance, can instantly push the wrong accumulator over the line.
You are fast, but you are highly inaccurate.
Conversely, if the task requires precision and there is no time limit, the brain adopts a conservative policy. It sets the stopping bounds very high. It uses deep buckets.
Now, the decision takes much longer to execute, but over that extended integration time, the random spikes of leftward and rightward noise statistically cancel each other out.
Exactly. The underlying drift rate, the true signal from the MT neurons, is allowed to steadily accumulate until it reliably hits the correct upper bound.
Your reaction time is slow, but your accuracy approaches perfection.
This mechanical model doesn't just predict error rates, though. It actually explains the subjective psychological feeling of confidence.
Wait, really? The feeling of confidence?
Yes, when you make a decision, your internal sense of confidence is directly derived from these two variables: how far apart the bounds were set and how long it took the random walk to hit the threshold.
So a fast hit on a wide bound feels like absolute certainty.
Exactly. The drift diffusion model is a triumph of mathematical psychology. It perfectly predicts the reaction times and the error curves of the monkeys in Newsom's lab.
But neuroscientists are not satisfied with mathematical abstractions, are they?
Never. If the brain is literally performing calculus integrating a variable over time to a bound, there must be a physical network of neurons actually doing the integration.
We have to find the actual buckets in the brain.
Yes. And to find them, we have to leave the visual cortex entirely. Area MT only provides the momentary drops of water.
We have to follow the anatomical projections downstream, deep into the association cortices, specifically into a region of the parietal lobe called the lateral intraparietal area, or area LIP, and regions within the prefrontal cortex.
Now, if you're listening to this and wondering how a single cell in the parietal cortex knows to act like a calculus student integrating variables, the answer lies in the biophysics of recurrent networks.
Because area LIP neurons are profoundly different from the sensory neurons in area MT, right? MT neurons only fire when a visual stimulus is physically present on the retina.
Right. But LIP neurons exhibit a property called persistent activity.
This is exactly what Mountcastle was desperately searching for in the somatosensory cortex and couldn't find.
Exactly. LIP neurons and neurons in the prefrontal cortex are wired together with dense, recurrent excitatory collaterals.
So when one LIP neuron fires, it excites its neighbors, which in turn feed back and excite the original neuron.
Yes. Furthermore, their synapses are rich in NMDA receptors, which have very slow decay kinetics.
Meaning that once a network of LIP neurons is triggered, they can keep each other depolarized, sustaining a high firing rate for several seconds, even after the initial sensory input has completely vanished. They can hold a state.
But they don't just act like a simple on-off memory switch. They don't just hold a static rate. They actually have the capacity to act as accumulators.
They can hold a baseline firing rate, and then, as new momentary evidence arrives from area MT, they smoothly ramp up or down their firing frequency.
They are the physical embodiment of the rising water level in our buckets.
To prove this, researchers recorded from individual LIP neurons while the monkey performed the random dot task.
Importantly, LIP is anatomically linked to the superior colliculus and the frontal eye fields. It is deeply involved in the motor planning of saccades rapid eye movements.
Since the monkey indicates its choice by looking at a left or right target, LIP was the logical place to search for the decision variable.
And the data, which is shown beautifully in figure 56-8, is breathtaking. When the monkey is watching the dots, area MT is firing its noisy momentary signals.
Simultaneously, the firing rate of the LIP neuron corresponding to the chosen target begins to steadily climb. It physically forms a ramp on the graph.
The slope of that ramp perfectly matches the calculus of the drift diffusion model.
If the motion is strong, say 50% coherence, area MT is pumping out a massive bias.
Consequently, the LIP neuron's firing rate shows a steep, rapid trajectory upward. The bucket is filling quickly.
If the motion is weak, say 5% coherence, the MT signal is incredibly noisy and weak.
The LIP neuron still ramps up, but the slope is shallow and erratic, taking much longer to rise.
But here is the ultimate test of the theory. We hypothesized a stopping bound in our bucket analogy, a threshold that triggers the action. Does that bound physically exist in the firing rates of the parietal cortex?
To answer that, you have to change how you look at the data. Usually, neuroscientists align their graphs to the start of the visual stimulus.
Right.
But if you shift the alignment to the end of the trial specifically, the exact millisecond, the monkey's eyes begin to physically move toward the target. A universal neural signature reveals itself.
This is the absolute mic drop moment of the chapter.
It really is.
It doesn't matter if the decision was easy and the monkey reacted in 300 milliseconds.
Yep.
It doesn't matter if the trial was incredibly ambiguous, purely 0% noise, and the monkey deliberated for a full 1,000 milliseconds.
Regardless of the slope of the ramp, the firing rate of the LIP neuron always invariably hits the exact same peak level of activity just milliseconds before the eyes dart.
That common peak firing rate, roughly 60 to 70 spikes per second in these specific cells, is the literal biological proof of the stopping bound.
It is the threshold. The brain continuously integrates the noisy evidence from area MT into the recurrent networks of area LIP until the population firing rate crosses a critical biophysical threshold.
And the crossing of that threshold instantly triggers the downstream motor circuits in the brainstem, initiating the saccade and terminating the cognitive deliberation.
Yes.
I want to pause and just marvel at that for a second. You can surgically place a microelectrode into the parietal lobe of a primate, and by monitoring the firing rate of a single cell on an oscilloscope, you can watch the animal make up its mind in real time.
It's incredible.
You can literally watch the physical manifestation of a thought climbing toward a threshold, and the instant it hits that invisible biological ceiling, boom, the eyes dart. The decision is executed.
Now, in the spirit of scientific rigor, we must acknowledge that this is an active area of intense debate. Not every neuroscientist agrees that area LAP is the sole locus of the abstract decision variable.
Oh, really? What are the dissenting theories?
Some argue that LIP is primarily a motor preparation area. They argue the actual cognitive decision might be computed elsewhere, perhaps in the prefrontal cortex or the basal ganglia, and LIP is simply reflecting the final common pathway preparing the eye muscles to move.
That distinction makes sense. Is it a cognitive accumulator or just a Modi clutch waiting to be released?
Exactly. But the textbook emphasizes that this ramping to bound architecture is not just a quirky anomaly for eye movements, it appears to be a universal computational mechanism.
Right. The text notes that if a monkey is trained to indicate its decision by reaching out with its arm instead of moving its eyes, the ramping activity shifts to a different parietal region called the medial intraparietal area, or MIP.
And if the task requires grasping an object with the hand, the accumulation is observed in the anterior intraparietal area, AIP.
So the anatomical location shifts depending on the required motor output, but the computational algorithm, the integration of noisy evidence to a physical threshold, remains identical.
It does. And to close the historical loop we opened an hour ago, what about Vernon Mountcastle, the man who started all of this with his vibrating fingertip experiment and failed to find the missing memory trace?
Right. What happened to his theory?
His legacy was vindicated by his own student, Ranulfo Romo. Romo took up the mantle of the fluttering fingertip task. He realized Mountcastle was looking too early in the sensory pathway.
So he moved his electrodes out of the primary somatosensory cortex and probed deeper into the frontal lobes.
And there, in the prefrontal cortex, he finally discovered the missing neurons. He found cells that exhibited the precise, persistent activity needed to hold the memory of the F1 vibration across the silent delay, maintaining the firing rate, so it could be mathematically subtracted from F2.
The mechanism of persistent activity and bounded integration isn't just a trick for visual motion. It seems to be the fundamental currency of higher-order cognition.
It really does.
Well, we have excavated an immense amount of neurobiology today. Let's trace the arc of Part A.
Sounds good.
We started by dismantling the colloquial idea of cognition, defining it instead as the biological decoupling of stimulus and response contingency and freedom from immediacy.
We traveled back to psychophysics to establish that our internal representation of reality is inherently noisy, requiring a decision criterion.
Then we found the source of that instantaneous noise in the direction-selective columns of area MT.
We explored the calculus of the drift diffusion model to understand how the brain handles that noise over time.
And finally, we physically located the brain's accumulators in the recurrent networks of the parietal cortex, watching a neural firing rate ramp up and smash into a hard biological threshold to trigger a physical choice.
We have managed to trace the continuous physical path of a simple cognitive decision from the arrival of photons on the retina all the way to the execution of a motor command.
But as we established at the beginning, understanding these sensory decisions is just the scaffolding for something much larger.
It is. I want to leave you with a profound question derived directly from the implications of this text. We've just established that deciding the direction of moving dots is simply the mechanical integration of cellular noise hitting a firing threshold in the parietal lobe.
Right.
If that is biophysically true, is that all a thought really is? Is human cognition at its absolute core nothing more than a provisional plan to act, bubbling up in a recurrent pool of neurons until a physical threshold is inevitably crossed?
That is a staggering reality to confront as you go about your day. Is every belief, every choice, every fleeting thought just a bucket of biological static overflowing in the dark?
It's something to think about.
Well, thank you for joining us for this deeply technical exploration. In the second half of this deep dive, part B, we are going to step out of simple sensory perception entirely.
We will explore how the brain utilizes this exact same ramping and threshold machinery to weigh abstract concepts, to calculate subjective value like choosing between an apple and a grape.
And ultimately, how this bounded accumulation mechanism might serve as the very biological foundation of conscious awareness itself. Join us next time as we continue our deep dive into Chapter 56.